All right.
Yeah.
I'm now starting the broadcast.
The broadcast is now starting. All attendees are in listen-only mode.
Hi, can you hear me? Hello?
They can't tell you. We hear you, but the audience can just listen.
They won't be able to respond right now.
Mute on. Yes, I'm mute. Can't unmute. Hi, hello, good afternoon. Can you hear me?
Yes. Yes.
Yes, good. So I would like to welcome you all on behalf of the YES online events working group and the whole YES Council to this first webinar about the scientific background of the YES Council members. I'm glad to see that there are few people who joined us this afternoon. And just to briefly remind you about the whole concept, I would like to mention that the idea behind these meetings is to that all the council members will give a short introductory presentations on the scientific background, current projects they participate in, and this is just to let you know about us, about our current work. So today we'll have 3 presentations. The first presenter is Julia Keller. It's my colleague from the YES online events working group. Her presentation is about the extratropical transition of tropical cyclones and impact on predictability. It sounds quite complicated, but I hope Julia will explain us what her research is about. So, Julia, can you start, please?
Yes.
Julia?
Can you give me the presentation?
Okay.
Okay, perfect. So I guess you have to mute all the participants.
I can't unmute Tobias. I don't know why. Hello, can you hear me? Hello? Julia, can you hear me? Julia? Julia, can you hear me now? Julia, can you hear me?
Your sound is very good, but Julia sounds not good.
Okay.
Okay.
Do you hear me now?
Now it's better.
Oh yes, now it's
Yeah, it's better.
Okay. So, okay, then I'll start with my presentation. Sorry for the brief delay. So, as introduced by Jakub, I want to talk about the research I've been doing in the last years, which is about the extratropical transition of tropical cyclones and its impact on predictability. So, at a brief background, I obtained my master and PhD degree at the Karlsruhe University of Technology, Karlsruhe Institute of Technology in Germany. Thereafter, I worked as a postdoc with the German Natural Meteorological Service, and since June, I'm now at WMO in Switzerland. So for today, I want to start with a brief definition. So most of you may know about it, but some may have a different background. So we'll briefly define what we mean by a tropical versus an extratropical cyclone. So you see here two satellite images. On the left-hand side, you see a typical tropical cyclone, which is Typhoon Chavan in this case. A tropical cyclone develops in the tropics or in the subtropics. It has a really nice symmetric appearance. If it's a strong storm, you see the formation of an eye in the center, and the center is also warm, a warm core. So you have a big blob of warm air through the entire troposphere here where the storm is. In contrast, an extratropical cyclone develops mostly in the extratropics, and you have a clear asymmetric appearance with some frontal structures like this and this here, and the system also has a cold core, so you don't have this blob of warm air in it. And so for me, coming from Germany, you may now wonder why we are caring about tropical cyclones in Europe, because they are often far away from us. But one answer to this is the extratropical transition of tropical cyclones. So what does that mean? So here you see a typical track of a hurricane that underwent extratropical transition in 2010, Hurricane Earl. You see the track here, so it just passed North America, and when it is here on the strongest intensity, you still see the quite nice symmetrical structure, but when moving in time, you see the system becoming more asymmetric, and in the end it completely transformed into an extratropical cyclone with frontal structures overall. So there is a conceptual model which is derived from the appearance in satellite images, and it basically shows how this symmetric warm core tropical cyclone transitions into an asymmetric and cold core extratropical cyclone with a frontal structure and this huge cirrus shield here on top. So, and the possible impact of such an event on Europe stems from the fact that about 36% of the North Atlantic tropical cyclones, this means hurricanes, undergo extratropical transition. This means that they transform from the tropical into an extratropical cyclone, and at the same time they interact and may also modify the mid-latitude flow. And the possible impacts on Europe we may experience is, on the one hand, that a transformed tropical cyclone may reach Europe as a re-intensified extratropical cyclone, like, for example, Hurricane Gonzalo did in 2014. And I'll get back to Gonzalo later. And the other, much more common issue is that a former tropical cyclone may modify the mid-latitude flow and may enhance the possibility for cyclogenesis, or for the development of new cyclones in downstream regions. And I want to talk a bit more about this fact. So here is a kind of schematic what happens. The tropical cyclone may develop in the tropical ocean basin, so just west of Africa. Then it proceeds westward in the beginning, and then at one point in its life it may start to undergo recurvature and move northward. This black line now indicates the kind of the mid-latitude flow, so that goes in circle around the northern hemisphere in this case. And if the tropical cyclone now starts to move northward, it may impact the mid-latitude flow by amplifying it, so it on the one hand lifts the tropopause and also pushes the mid-latitude flow to the north. And this is basically done by the outflow of the tropical cyclone. So tropical cyclone means you have some air moving from the bottom to the top of the troposphere, and at the top of the troposphere you have a strong outflow of air, which also is captured by the satellite imagery. And this strong outflow may now push the mid-latitude flow northward in this case, and you see the development of a kind of a trough here and a ridge over the Atlantic, and further downstream you have the development of another trough. And this another trough may now enhance the possibility that other cyclones form further downstream, like here, for example, over Europe. And how this looks in real data, I want to show with this example. So this is for Typhoon Choiwan in 2009. It's a typhoon. This means the storm took place in the western North Pacific. But in principle, the processes are kind of the same also for the Atlantic. What you're seeing here in colors is a representation of the mid-latitude flow. So you have this kind of ridge and trough structure here over the Pacific. So you have here Japan, here Korea, China, and Western North America. And the black lines indicate the mean sea level pressure, which basically show cyclones. And we have Typhoon Choiwan here now undergoing recurvature and starting to interact with the mid-latitude flow. When I click through it now, you see that there is a trough forming in the mid-latitudes, and Choiwan, a really strong storm, is moving ahead of this trough. So it approaches Japan. Now the storm starts to weaken. When I go back again, you see the amount of the minimum sea level pressure increases again, so the storm becomes weaker. This continues, and then in front of this trough, it starts to interact with this extratropical disturbance that is already here. And then the systems start to intensify strongly. And at the same time, you also see that there is a broad but weak trough over the central to eastern Pacific. And when we go further in time, we see that this trough is further amplified, and we get the development of a really strong ridge here over western North America. And ahead of this trough is another cyclone developing, as I said before. So, and this cyclone then approaches western North America. So that's one example, and the same we also see sometimes over the Atlantic. And during this interaction between the tropical cyclone and the mid-latitude flow, there are several aspects that are really important. So one is the phasing between the tropical cyclone and the trough. This means we have a pre-existing mid-latitude wave train or a pre-existing mid-latitude trough, as we have just seen, this kind of trough here. And then we have the tropical cyclone, and it really matters where the tropical cyclone moves towards this trough. So if it moves ahead of the trough, where you typically have lifting of air, you have the possibility for a stronger intensification. Instead, if the tropical cyclone rather moves to the tip of the trough or even behind the trough, then the chances for a stronger intensification and also for the impact on the mid-latitude flow is lower. And during this interaction, we got a variety of physical and dynamical processes involved. So on the one hand, we have the circulation of the TC itself. So it's a cyclonal circulation against the clock in the northern hemisphere, which may push parts of this trough further to the south, and with this amplifying the trough. On the other hand, we have the outflow of the tropical cyclone at upper levels, which impinges on the tropopause. It lifts the tropopause and also push it north, and push the amplification north, as we said before. And the circulation of the tropical cyclone also advects warm and moist air towards the baroclinic zone, so the kind of where you have a strong temperature gradient in the atmosphere or in the troposphere between the southern subtropical regions and the northern extratropical and polar regions. And this variety of processes and their interaction make an extratropical transition a challenge for current NWP models, so for current weather prediction models, and also for forecasters. And the impact of such an event can be visualized by investigating an ensemble forecast. So you start one, please mute your microphone over there. Thank you. So we start with one forecast and add small perturbations to the initial beginning, and then we run the forecast model for about 10 days or whatever. And with this we get, for example, 5 different simulations on how the development will look like. And this plot now shows you for Hurricane Gonzalo one of these ensemble forecasts that were initialized prior to the storm's interaction with the mid-latitude flow. And what you see is one isoline for the geopotential height, so in principle one representation for these troughs and ridges in these 50 forecasts. You see in the beginning the lines are really close together. When we now move further in time, you see that they are starting to separate a bit from each other, but they are still quite close together over Europe. Then we have here tropical cyclone Gonzalo moving into the mid-latitudes, starting to interact with this broad trough here. Over Europe, you see we still have a really good forecast because all of the 50 representations are close together. And when we now proceed with time after Gonzalo impinged on the mid-latitude flow and merged with it, we see that we got a strong increase in the uncertainty of the forecasts over Europe, and about 5 days, in a 5-day forecast, we would not have any clue on the particular shape of the trough over Europe. And you see that we have a really strong uncertainty that resulted from the ET of Gonzalo over Europe in this case. And so that's why we care about tropical cyclones in Europe, because when they are undergoing extratropical transition, they may strongly influence the mid-latitude wave pattern. They may reach Europe as a strong extratropical cyclone and may trigger the development of a wave train that favor the development of cyclones in further downstream regions. And it often, at the same time, coincides with a reduction in predictability. So in these cyclones that develop downstream or the former TC may have a potential for high-impact weather events over Europe, but at the same time, these events come with increased uncertainty, so making it really hard to predict them. And my research was basically dealing with this fact, and we were raising the question on how to improve the forecast during extratropical transition. And this means we need a detailed understanding of the important processes that go on during the interaction, so what are the important aspects. And then we also have to investigate how they are represented in numerical weather prediction models. So if the models are able to capture them right. Another issue is that a tropical cyclone is often a really small system having a diameter of 100 kilometer when it's with its core of 100 kilometer when it's still in the tropics. And we have the rather large-scale mid-latitude flow, so we also do have a kind of different scales that are interacting. And the research we were conducting is basically using modeling experiments, so running a numerical model. There you can, for example, take out a tropical cyclone and see what happens without, so you can assess the contribution of the tropical cyclone to the amplification of the wave trains. You can use various analysis techniques, for example, analysis of the eddy kinetic energy budget to see the impact of the tropical cyclone. And of course, you also do some field campaigns or observations to get observations on this process to better understand what's going on and also to compare your models with. And with this, I hope that I gave you a quite interesting overview on this topic. And if you have questions, I'm really happy to answer them. Thank you very much.
Yes, thank you, Julia. We have time for some questions, so if you have one, please raise your hand. Or you can type it in the chat box.
Or you can also send me an email afterwards if you want to.
All right. If there are no questions, oh yes, Marisol.
Hi Julia, thank you for your presentation, was really interesting. Do all the cyclones can amplify or generate extratropical cyclones, or there is a need from some kind of threshold in the intensity of these cyclones to be able to do it?
Okay, so there is no real link to the intensity of the former tropical cyclone, so that it can be a really strong tropical cyclone that has no impact, but it can also be a rather weak tropical cyclone that may have a really strong impact. So the more important aspect decide the intensity of the storm is this kind of phasing, which I told between the trough and the cyclone. And of course also if the cyclone, so the tropical cyclone has to still be quite strong and not completely decaying when it enters the mid-latitudes. But it doesn't matter how strong it was before, eventually.
Okay, and another question, sorry. In your opinion, which component of the models we need to put more attention if we want to improve the representation of these kind of transitions?
So a really important component are moist processes. So for example, when you have the tropical cyclone pushing moist and humid air, moist and warm air into the mid-latitudes, then you have the formation of so-called warm conveyor belts, so of regions of where warm air is ascending. And there are currently research conducted on how this is represented in numerical models. And of course, it also depends on the resolution of the model. So if you have a really good horizontal resolution, let's say of about 5 kilometers, your model will be doing quite well with this, but the most global models are currently running with 15 to 20 kilometers. So there some of the processes are represented already, but of course when you increase the resolution, representation would become better.
Okay, thank you, Julia.
Thanks, Marisol.
Thank you.
Are there any more questions? All right, if there are no more questions, thank you, Julia, for your interesting presentations. And then we'll go to the next one. The next presenter will be Kevin Reed from Stony Brook University, USA, and he will present the presentations entitled High Resolution Climate Modeling. So, Kevin.
Awesome. Thank you for that introduction. You can see my screen okay?
Yes, we can.
Okay. All right, so I'm going to kind of give a brief overview on some work that I've done on high-resolution climate modeling. Just a quick background is I did my PhD at the University of Michigan. Afterwards, I spent about 13 months actually as a science policy fellow for a United States senator before I moved on to the National Center for Atmospheric Research to do my postdoc, and now I have been at Stony Brook University for just over a year and a half as an assistant professor, where I am starting my own research group to look at high-resolution climate modeling. But I'm not going to list them here, but a lot of these runs require millions of computer hours to do for one run, and so it would be unfair to not mention that this required many collaborators to get a lot of this type of research done. Some initial points I'd like to make is that it's my opinion that we're entering an era where climate models, and when I say climate models right now, I'm really referring to AGCM, so this is the atmospheric component of general circulation models or system models, are really approaching the same, approaching weather scales. So high resolution global climate modeling, which I kind of define here to be less than 30-kilometer grid spacing globally, will greatly improve our ability to model multi-scale phenomena, as such we just learned about from Julia and tropical cyclones, as well as to project regional impacts of climate change. So together, this can and will, in my opinion, have many applications to other scientific disciplines and to local communities. But I'm not going to necessarily get into that today. So what is really kind of the cutting edge aspect of stuff that we can do with climate modeling? Well, the idea is that we're approaching the era in which we can simulate a lot of different types of extreme weather. So in the middle, you have a kind of at the bottom and the top, you have examples of floods and droughts, and those have maybe been able to be captured in typical, to a certain extent, in typical CMIP, IPCC versions of the model. But really, as we go towards these high resolutions, we're able to capture things like tropical cyclones, maybe mesoscale convective systems and severe weather, maybe snowstorms. That's kind of a new area that's been starting to be looked at. But we're definitely far away from capturing individual tornadoes. But we are getting closer to be able to look at kind of high convective weather events in general. So just a little bit more motivation. This comes from the United States National Climate Assessment. That changes in extreme weather events are the primary way that people most experience climate change. And so human-induced climate change has already increased the number and strength of some of these extreme events. And over the last 50 years, much of the United States has seen an increase in prolonged periods of excessive high temperatures, more heavy downpours, and in some regions, more severe droughts. And so the idea is that this is one of the true applications of high-resolution climate modeling, is to try to understand if there are trends in these type of extreme events that require really either long periods of observations or climate models that can be run for hundreds of years to really look at. So just one last slide to kind of get you into context of what I'm talking about. So here's just kind of the plot that you've seen some version of before, I'm sure before, that shows the scale of spatial scale in the atmosphere as well as temporal scale. So if you kind of focus up on the upper right corner, this has kind of been the focus for a long time of climate models, which is trying to get climate variation, ENSO and seasonal cycle. So they operate at resolutions that are typically over 100-kilometer grid spacing. And then traditionally, at least for the last decade, this has been the scale that our weather models interact with. So they don't run as long. They maybe run a week or two. And they typically get down to scales on the order of maybe 10 kilometers in grid spacing. So they can capture certain things such as cloud clusters and organized convection, squall lines, tropical cyclones, as you see here. And the key here is kind of the current generation of high-resolution climate modeling is kind of focused on this area. So it's really going the old traditional route of climate modeling, but it's really pushing the resolution down. And when you do this, if you kind of just focus on kind of the middle part here, the first really main things that kind of jump out when you go to high-resolution climate modeling is tropical cyclones as well as frontal systems. And so here's just another way to look at this. If you had a typical CMIP version of the model, which is all the way over to the right, this is a photograph, a pixelated photograph of what Hurricane Sandy would look like in outgoing long radiation at a typical CMIP resolution. And as you go to high resolution in the bottom row, which is 0.5, which is roughly 50-kilometer grid spacing or 25-kilometer grid spacing, or all the way down to 14, which is what maybe current operational global forecast models use. You can see that you're starting to resolve the processes that are important to that tropical cyclone much clearer. So some of the work that I have done has been using the NCAR community atmosphere model in multiple different configurations, but the main thing to focus on is we kind of test the model in AMIP mode, which is just prescribed boundary conditions from the ocean, so there's no interactive ocean. But we generally kind of run the model at 100 kilometers, which is your typical CMIP resolution. And then we also run it at what we call next generation high resolution. So this is 25-kilometer grid spacing globally. So these runs, one 30-year simulation can generally cost around 5 to 6 million computer hours and produces about 200 terabytes of data. And so we've also been starting to do now future warming scenarios starting in 2070 through, this should be 2099. And everything here is typically just prescribed SST, ozone, CO2, and solar forcing. So these are all basically prescribed boundary condition runs. So what does that provide us? So here's just kind of a snapshot that I've included a link to a YouTube video that shows these high-resolution results. But this is just a plot of basically total integrated water vapor and you can kind of see at 25 kilometers, you get a lot of detail that starts to pop out, particularly if you focus on the tropics. You'll notice in the North Atlantic and the Pacific there are multiple tropical cyclones that exist, but you can also see that kind of in the region of the ITCZ, you can see this really intense convection. And if I was to put this in motion, you could actually really see the role that topography plays, particularly in the Andes and the Himalayas, in kind of blocking atmospheric circulation in those regions. And that's another improvement from going to high resolution, is that you better capture the appropriate height of topography. So what does this mean? We've done a lot of stuff to look at the improvement as you increase resolution, to look at extreme precipitation. So really if you just focus on CONUS, so the continental United States, which is the bottom right, you'll see that in gray are the observations. So there's numerous observation data sets through different types of methods, satellite and gauge data sets that exist, but that shading is the gray, and you can see as we go from basically low resolution, which is the green, to CMIP resolution, which is the red, to this 25 kilometer grid spacing, we're really inching up into the actual observations in terms of extreme precipitations, particularly when you focus on these really extreme rare events down in the right-hand corner. And this is true. We've looked at it globally and used different types of data sets as well as just focusing on the tropics. And so some areas do better than the others, but some areas the observations are maybe a little less certain as they are over a longer record of observations in the United States. And you can also do other things such as look at the 20-year return value on precipitation. So really if you just focus on the bottom row, which is a low resolution, and you just focus on the colors and try to compare it to the upper left, which is observations, you can see that that the low resolution models just have the wrong colors in the wrong area. So they're just not getting these 20-year return values correct. But as you go to high resolution, you can, in the 25 kilometers in the upper right, you can really see that the colors are actually starting to match up regionally with what you had globally. And so this is great because this means that you can actually maybe start to project these changes in these particular regions if you do climate change experiments. Here is a plot of a 1 kilometer or 100 kilometer simulation. So this is a typical CMIP run, AMIT mode. And so this is a plot in 26 years of all the tropical cyclones that are tracked in that model. So you can see there's not very many. And if you just run the same run at 25 kilometer grid spacing, this is the number of tropical cyclones you get in a 26-year simulation. So if you just toggle between these, you can see that there's a big increase in storms and storm intensity, which is noted by the color, as you go to these higher resolutions. And so this gives us hope that maybe we can actually do climate change runs and try to look at how these tracks, intensity, and other characteristics of global tropical cyclones change. But it's worth to note that the model is not perfect. It's never been really tuned to do this type of research. And so if you focus on what observations look like, you can see there's definitely some significant issues with biases in location of storms as well as intensity. And that's something that's being continued to work on. The idea is that if we can improve the model climate, we should be able to improve some of these biases. This is really just a kind of a summary of all the high-resolution runs that have been done between NCAR and the Department of Energy in the United States at 25 kilometers globally. And so the idea now is that this isn't just one run or two runs that we have. We do now have generally about an order of 10 to 11 runs. And here's just showing you the interannual variability of tropical cyclone count in the North Atlantic. So you can see that some versions of the model, for whatever reason, are doing better than other versions. But we're kind of in the area now where we have enough ensemble runs that we can start to understand some of these. And one of the things that I currently look at with one of my own students is that the impact of African dust on tropical cyclones in the North Atlantic. And so we've looked at different behavior of different dust models. whether they're fully prognostic or prescribed, and the impact it has on tropical cyclones. And the idea here is that global models or system models now have fully prognostic aerosol models into them. And so this is it's been an active research question for over 2 decades, the impact of African dust on hurricanes in the North Atlantic, but it's been really difficult to actually study because we lack global models, or we lack any models that can resolve hurricanes as well as have fully prognostic aerosols. So we're entering an area where we can actually maybe look at fundamental science questions. And then finally, just finishing here, we can also start to do future climate scenarios. So these are time slice experiments, so everything is AMIP. So what we do is we take the sea surface temperature from a low resolution RCP 8.5 run, and then we use that to force our AMIP run, and then we can compare it to the present day AMIP run, which is the blue line. So if you just focus on the hurricane area in the center, and so this is just a storm count, you can see that the model does a decent job in the present climate, which is the blue box, to observations. It's at least in the same vicinity, and that as we go to an RCP 8.5 scenario, we see a pretty significant decrease on the order of at least 5 to 10 tropical cyclones, or sorry, hurricanes. So these are category 1 strength or higher every year in a warming climate. But if you focus on all the way to the right, there's almost a doubling of the major hurricanes. But this also does, if you compare this part, the major hurricanes, so these are the most intense, to observations, you can see actually this is where the model resolution is still not quite there enough to resolve the right number of category 4 and 5 storms, but it's still simulating a significant increase in those major hurricanes as you go to the future. And so I'm going to skip this one and kind of focus just on the North Atlantic and show you kind of where we're at in looking at these things regionally. So the top row are just current. This is tropical cyclone density for 3 different ensemble runs of the same, everything's the same except initial condition. And these are 26-year runs. And so you can see there is, depending upon the run, some pretty large range in where the tropical cyclones go. But if you focus on the next 3 below it, these are the similar ensemble for the future, RCP 8.5. And you can see that no matter, so there is also variation where the tropical cyclones are, but there is a robust decrease from the future, or from the present climate to the future climate in the North Atlantic in tropical cyclone location. But this is all dependent upon that underlying boundary condition of the SST. So if you focus on the right, all the way to the right, these are future scenarios in which we kind of use different SSTs from a low resolution run that maybe have more El Nino or La Nina-like. And you can see that there's definitely still a decrease from the current climate, but the pattern of where the storms are is a little uncertain across these ensembles. So there is a robust decrease, but the magnitude and location of that decrease really depends on your boundary forcing. So we have somewhere a long way to go. You can also look at other things such as precipitation associated with hurricanes and how that'll change. So here's just my final slide. We are starting to look at decadal simulations to high resolution in climate models. As the climate warms, the number of tropical cyclones is decreasing. However, the most intense storms are becoming more intense. And that decadal ensemble simulations are really starting to shed light on regional changes, at least in storm count. But the magnitude and pattern of these future changes remain uncertain. And so this is continued ongoing work. We have many data sets available, so if there is anybody who would be interested in maybe looking at some of this stuff for other extremes, you should definitely shoot me an email, and with that I'll finish. Thank you.
Thank you, Kevin. It's time for questions. I can see one hand up. Money? Money? Okay, are there any more questions? Yes, Money, go ahead. Hello? can you hear me? Mani, can you hear us? Can you type your question in the chat box?
Maybe.
Yeah. Yeah, so. Okay.
Well, if anybody wants to just shoot me an email, I can answer a question that way too. Might take me a few minutes or a few days to respond.
Yes, okay. Are there any more questions to Kevin? No.
Kevin?
Yes?
Yeah.
Kevin, one of your one of your images I was having a problem seeing, so
Okay, can you introduce yourself?
hello, I don't know, just now what is wrong? Okay, you were showing us oh boy.
Yes, we can hear you.
Yeah, we can hear you. Go on.
Okay, I didn't see this properly. You were showing us the North Atlantic distribution.
Yeah.
I really wasn't. Oh, my screen's gone long. Oh, right. Okay, sorry. You were the slide with North Atlantic distributions. You were trying to show us how there was a robust decrease in the storms in the North Atlantic, but the magnitude of the decreases dependent on sea surface temperature. I was having a problem seeing these things because maybe it's really small, but I saw the color changes, but I'm not seeing what I guess I was having a problem seeing this on the screen.
Yeah, so if you were, so I think I have the slide back up that you're talking about right now. Yeah, and so, yeah, so for these three ensembles, kind of on the second row in the middle here on the left, yeah, so from there, it's hard to see if there's probably not a change in count. But if you focus on these two, what are with the title of alternate SSTs all the way over to the right, especially if you focus on the one that's all the way over to the right, you can see that there is definitely a noticeable increase in number of storms from the other future scenarios. But yes, I agree. These are just densities, right? So it could also just mean that tracks are lasting longer. But if we also look at counts, which I'm not showing here, you can see the decrease.
Okay, so that's just distribution. Those colors are just showing you distribution. Okay, so
yes, that's just basically a track density.
Oh, all right, density. Okay, all right, now I see. All right, thanks.
Yep.
Okay, thank you for your question. Are there any more questions? Okay, I guess there are no more questions. Thank you, Kevin. And the last presenter for today is Ariane Frassoni dos Santos from Center for Weather Forecasting and Climate Research in Brazil. She will tell us about development of the air quality forecast system for the Olympic Games in Rio de Janeiro. Ariane, can you hear me? Ariane?
Yes, can you hear me?
We can hear you now. Okay.
Hello?
Let's start. Go ahead.
Yeah, okay. Okay, thank you for the introduction. So, I'm Ariane from Brazil. I'm working at Center for Weather Forecasting and Climate Studies of the National Institute for Space Research in Brazil. And I will briefly give you an overview about this work that we have been doing since April to implement the air quality forecast system for the Olympic Games in Rio de Janeiro. The Olympic Games finished in about 1 week ago, and we have a very short time to implement the system specific to the Olympic Games. And we had collaboration of several people here at CPTEC and from the University of South Brazil and the University of Rio de Janeiro. And I will give you a short background. I got my master in meteorology at INPE and my PhD as well. And I finished my PhD 2 years ago. And I worked in my PhD with numerical methods applied to the convective parameterization regional model that we are developing at CPTech. And now I'm a research assistant at INPE since last year, leading the modeling, development, and research in the Brazilian developments on the regional modeling system that started its development at Colorado State University. Now, my contribution with the YES community, I'm a local representative with focus in Brazil, and I'm working with the working group, online events, and outreach working group as well. So this presentation, I will give you some aspects of the BRAM's unified version, the last version that we released in this year, in March, and the air quality forecast system for the Olympic Games in Rio, and final remarks. So the Brazilian developments on the RAMS model, we are in the version 5.2, and this model is used at CPTech to regional to scale, local scale forecast for air quality forecasts and weather forecasts. So now we have an online and a fully coupled surface and chemistry model in the BRAMS model, and with several physics and dynamics aspects included in this version, like monotonic advection for scalars to moment cloud macrophysics, the convective parameterization developed in scale aware by Brian Freitas, 2014, and we implemented the JULES surface model with urban surface scheme and the Nakanishi-Nino turbulence scheme. We running the BRAMS model with a fully massive parallel system using MPI. And we have now two different radiation schemes to represent radiation processes. The model Karman RTMG. And we recently implemented the matrix aerosol model from NASA. But this model is now not in operation yet, and we are evaluating this model. Recently, the main research associated with BRAMS model, Dr. Saulo Ribeiro de Freitas, he moved to NASA in the end of last year, and he published with several collaborators the last paper in GMD about this new version. This paper is in the discussion version yet. So the BRAMS model we are running for air quality and weather forecast, and this model provides forecasts for some species like carbon monoxide, oxides of nitrogen, ozone, particulate matter, and all for 3 days in advance with 25 kilometers with grid spacing. And for operational systems, we have the BRAMS running in 5 kilometers to weather, just to weather forecast without chemistry, because the computational power is not enough to run with 5 kilometers of all South America for air quality, and we run BRAMS for 7 days, sorry. And the air quality, we are running for 3 days with 25 kilometers of grid space. And with the implementation of the air quality forecast system for Rio de Janeiro, we could improve our power to forecast in a higher resolution with 1 kilometer over region of Rio de Janeiro for 2 days, specifically to the Olympic Games. And with this improvement, we could include as well the weather and air quality forecasts for southeast Brazil, including the metropolitan area of São Paulo and Rio de Janeiro as an intermediate domain to move from the coarse grid in 20 kilometers to 1 kilometer grid to specifically Rio de Janeiro. And we are working to change the air quality forecast system in South America to 25 kilometers grid space to 20 kilometers grid space, increasing the resolution. Here we have an example of forecasts for South America. We can see the surface level of CO in the left and the right, 500 hectopascals of CO over South America. We can see in points of pollution from the megacities and all the biomass burning pollution. The biomass burning is the main problem of South America during the dry season. And the biomass burning pollution influence the other regions because the circulation of the pattern circulation over South America. We can see here the transport of the biomass burning pollution to other regions like South Brazil, Northeast Argentina, Southeast Brazil, and this is a very big problem to South America associated with air pollution. And one very important point to air quality forecast system is the preprocessors of trace gases and aerosol emission fields. And this is a tool that we are using, the PrepCam source, that is specifically to get the initial data for the air quality model. And we have several sources of air pollution, like urban, industrial transportation, biogenic, biomass burning, volcanoes, and biofuels, with different databases, like the global databases like Retro and Edgar, and we have a specific inventory to South America developed by the Alonso et al. In 2011 that increases the resolution of mainly the urban pollution over megacities for carbon monoxide and NOx. And you can see different databases for different kind of sources. Specifically to biomass burning, we have the 3bin developed by Freitas et al. In 2005 and Longo et al. 2009. An improvement of this model to get the information about biomass burning from Pereira et al. 2009. So for the Olympic Games, we had the necessity to improve the preprocessor emissions specifically to Rio de Janeiro, because in a higher resolution, like 1 kilometer, the global inventories are not enough to characterize the details of the pollution over megacity. So one important point was to develop a specific emission source to Rio de Janeiro, and according to a paper from Pinguelli et al. In 2011, the main source of pollution in Rio de Janeiro is the vehicles. So the vehicles of the city is a very big source of pollution. And with during the Olympic Games, one point is to better predict particulate matter in the carbon monoxide for the city, mainly for for sports and for the visitors in the city. And we had information about several Summer Olympic cities like Atlanta, Sydney, Athens, Beijing, London, about the distribution of particulate matter. But we didn't have information about this kind of pollution for Rio, and we did some studies to understand how the pollution is in Rio, to provide better information about the air quality forecasts. And one important point is the particulate matter in Rio is associated with the pollution from heavy vehicles like trucks. So we had a challenge to increase the resolution from 20 kilometers over South America to an intermediate domain of 5 kilometers in southeast, including the metropolitan region of São Paulo, and a big region of Minas Gerais state, Rio de Janeiro, and Espírito Santo. And to improve the resolution over the Rio, we used mainly the metropolitan region of Rio de Janeiro, that I show here. And this is the CO forecast for a specific day. And for the 1 kilometer resolution, we used the initial conditions and the boundary conditions from the intermediate domain. The difference between the configurations of these three different domains are basically microphysics and radiation. We couldn't use the new radiation RTMG that is implemented in the 5 kilometers over South America, because the interactions between radiation and aerosols are not well developed. So we are working to improve the feedbacks between radiation from RTMG and the aerosols. So we used the old model for radiation, and the 20 kilometers and 5 kilometers we used a deep convection turned on and turned off for the 1 kilometer. So the main problem was to work with the emissions for the metropolitan region of Rio de Janeiro. That we got information about the street maps of the Department of Traffic of the district of Rio de Janeiro to improve the emissions, distributing the pollution over the streets, the main streets, and you can see in the right the emissions of CO and NOx. And you can see perfectly the distribution over the main streets of Rio de Janeiro of the emissions. And we could improve the resolution of the emission sources in our two PrepChem sources, preprocessor emission. And another challenge was to implement an urban parametrization in the new version. This work was done by Batista da Silva in 2016 in her PhD thesis. She implemented the 2T scheme of joules in the BRAMs, in an old version of BRAMs, to understand how the Haiti Island how Haiti Island is described over metropolitan region of São Paulo, and we got her work to implement in the new version of BRAMs to better understand the complexity of geometry of urban areas. And we know that the energy budget is different from vegetation areas, so it is really important to have a urban parametrization in a higher resolution like we use it for Rio. So, and another step was to improve the 2T scheme of joules, implementing biophysical parameters like albedo, emissivity, and Lie to better represent the information for the urban parametrization. So this work was developed by researchers at the University of Rio de Janeiro. They characterized these parameters to 2012 with mean and standard deviation information about these parameters, and they implemented for different classes of land use and cover soil to joules classes. They are 9 different classes, and we implemented another one to activate urban parametrization called urban hoof. And we could, with all these implementations, we could improve the air quality forecast for the metropolitan region of Rio de Janeiro. Here you can see the near surface ozone over the metropolitan region of Rio de Janeiro, valid to 90 UTC of 17 August 2016. And we didn't finish the validation, but we started to verify the skill of the model. We don't have a robust statistical validation yet. We are working with this now. And just to see here, one buoy over the sea near Rio de Janeiro to compare the wind speed over this region. The dots are the information observation, and the lines are different runs of the BRAMS model. And we could see the BRAMS had a very good representation of the observations. And here some validation of sea surface, temperature, air temperature, compared with another regional models that are running here for the Olympic Games, the WRF model over metropolitan region of Rio de Janeiro, and ETA model. And we could see that the BRAMS has yet bias in the representation of temperature and the dew point temperature, and we are working to improve the representation of these meteorological variables to better represent weather forecast for this region. So, as final remarks, we need to adjust the new version, mainly to weather forecast over Rio, but the results are promising. We have contact with local agencies like the main district of Rio to implement this system for Rio, for the state of Rio to provide information for the state, not only an information just temporarily during the Olympic Games, because we are continuing this implementation for the Paralympic Games that starts in 2 weeks. And we have the plan to provide this information continuously to the state of Rio de Janeiro. Thank you very much for your attention. Questions?
Yes, thank you, Ariane. Are there any questions to Ariane? I can't see anyone interested in asking questions. Okay, so if there are no questions, I would like to thank all the presenters, and I would like to thank the audience for joining us today. I would also like to thank our Apex colleagues for providing us with GoToWebinar, and I would like to apologize for the technical problems in the beginning. We are still learning how to use this tool. I'm sure the next time will be better. And finally, as I forgot to introduce myself in the very beginning, I would like to do it now. My name is Jacob Valavender. I'm a member of the online events working group, and it was a pleasure to chair this meeting for you. Also, I
didn't get your name.
Yes?
I didn't hear your name.
Sorry?
I didn't hear who you are.
Jacob Valavender.
Jacob?
Yes, exactly.
Oh, Jacob.
Okay, one more announcement. The next webinar of the YES Council series will take place on 21st of September, so please save the date and we will send you the details soon per email. So that's it for today. Thank you again, and bye-bye.
Bye. Thank you.
Thank you very much. Bye-bye.
Bye, thank you.